Okay, so a word about the exam. So there are a lot of theorems, and I don't really expect you to know them by number because I don't even know them by number. And the numbering in the book is somewhat arbitrary anyway. I mean, it's not like someone in a different textbook can number them differently. So the numbering of the theorems is not important. Okay, so if you're proving something on an exam, then you can just say this, like assume this, then we have this by a theorem, right? So you don't have to know the numbers of the theorems, okay? So we only have one named theorem. So usually you need to know the statements, like you need to, if it's a named theorem, then I'd be like, okay, well, you should know the statement of a named theorem for sure. So the only named theorem is the fundamental theorem of arithmetic, theorem 1.8. That's the only one that's named. So you need, if I say write down the fundamental theorem of arithmetic, then you ought to know that. But as far as like knowing them by number, like that's not an expectation that I have, because like I don't even know that. But if you happen to know some of them by number, like you might know, I don't know, what's one we use all the time? Theorem 2.1. Well, no, not that one. Let's see. Theorem 1.5 we were using a lot on this last homework, and so there's some you might know by number. If you do, you can quote them, that's fine. But like if you're not sure, you can just say like by a theorem that we have or something. So that's fine. Okay, does that help a little bit? Because I think that might have been a lot, like not knowing how to write things down. So yeah, so I think mostly I'm concerned about you knowing what results you have, like knowing what you have in your tool belt. Okay, not necessarily attaching a number to those. So, okay. So for today, we've got to finish proving theorem 2.8, and we need to prove theorem 2.9, and then theorem 210 is just like straight from theorem 2.9. So it's super fast. And then we're going to start chapter 3 today, hopefully, is the plan. So I want to get chapter 3. I want to get started on chapter 3 enough that we can have a homework due right after, like, the week after the exam. So we need to kind of get some traction on chapter 3 this week so that we can have a homework due. So we can review a little Monday, do the memory stuff, and then take the exam Wednesday, and then, kind of make some progress on chapter 3. So that's my plan. Okay, so theorem 2.8. Let's go on this. Okay, so I'll review a little bit of theorem 2. Oh, let me see who's here. We're missing Jose. And Benjamin. And that's it, right? Just so they know. Okay. All right. So here's theorem 2.8. And so this stated like this. So we have PS9. You may already have all this in your notes, so you don't have to copy it down again if you've already got it. And so we had proved that 1 implies 2 at the end of class on Friday. So now we are going to prove that 2 implies 3. Oh, hey, Benjamin. Okay, so that's where we're going. So I'm not going to redo the proof that 1 implies 2. I'll just go 2 implies 3. Okay. All right, so for this, we're gonna assume that 2 is true. So we're gonna assume and when I write down my assumption, I'm gonna change the letter from A to B because it's gonna be useful to me in my proof. So I'm gonna assume that for any B not equal to 0 in Z mod P, that the equation B x equal 1. So I want to assume that. So I'm going to assume that 2 is true. And then I also want to assume the if part of 3, right? So I want to prove that this statement is true. So I'm going to assume the if part and I'm going to go directly from there. Okay. And so we're also going to assume that BC equals 0 in Z mod P. All right. So what are the options here? So I have case 1 would be if B equals 0. If B equals 0, then we're done because we have one of our cases there, right? So we'll say if B equals 0, we have nothing to prove. We're done, or I don't know. I kind of have been saying we're done. So we're going to assume that B is not equal to 0. And where are we going to try to prove? So this is an or statement. So if we assume that B is not 0, then what do we have to prove to make this statement true? That C is forced to be 0, right? So if B is 0, then we've satisfied the or condition. If B is not 0, we need to prove that C has to be 0, and then this or is satisfied. Does that make sense? Okay, so that's where we're going. Okay, so how do we show that C is 0? Well, I've assumed that B is non-zero. Now look at my assumption that I have. What do I have to use there? Then there's some solution to this equation, right? So if B is non-zero, then there's some solution to this equation, right? So by assumption, there exists some element, I'm going to call it, I'll just do some W in Z mod P, such that B times W equal 1. So that's the inverse element, the multiplicative inverse of B in Z mod P. Okay, and so now what? Okay, so this is going to be kind of funny here, okay? So we're going to say, we're going to start with 0. And we're going to say 0. Well, what is 0 equal to? Okay, so let's see, how do we do this? Okay. So this will take a little bit of ingenuity. So you might not think to do this. So W times 0. And what's 0 equal to? Well, 0 is B times C, right? 0 is B times C. So that's W times B. Oh, I guess we have this kind of, well, anyway, I'm just gonna write them next to each other. That's times. Because 0 is B times C, right? Oh, maybe you can't see that online. That's what I've got so far. Well, since this is associative, I can say that that's equal to WB times C. And what's WB equal to? That's 1, right? So this is 1 times C. And that is equal to C. just C, right? So what have I shown? I've said, assume that B is non-zero, then what must be true? 0 equals C, right? So we've shown that C equals 0. So we can say, let's just, so thus, when B, C equals 0, either B equals 0 or C equals 0. Let me tilt that slightly so you can see all of that. Okay. So there's that. So we proved that 2 implies 3. Now I need to do 3 implies 1. So for 3 implies 1. All right, so do you remember, we want to show that this property is true and then get to that P is prime. Okay. Now, does this property look kind of familiar, like one of the theorems we had before about prime numbers? Kind of?
Yes.
What did we have for a prime number?
It has equal P and plus or minus 1.
Yeah, so that's the definition of prime. So P is prime if its only divisors are plus or minus 1 and plus or minus P, right? So that's the definition. But we had a theorem, Williams, do you remember?
If P divides BC, then P divides B or P divides B.
Yeah, and so this was actually, and if it don't, this was theorem 1.5, which you don't need to know the number again, but it's that P is prime if and only if P has this property. Right? So that kind of looks like what we've got here, because we have a B times C and then we have this thing, but we have that they're equal to 0 in Z mod. Yeah, so if 0 in Z mod P means that they are divisible by P, right? Yeah, so that's what we have. So that's what we want to do. So we're going to take this statement in Z mod P and convert it to a statement about being mod, right? About mod equivalence, right? And then we'll be able to prove this theorem is true. Okay. All right. So we're going to assume that we're going to assume that thing whenever okay, and then we want to, okay, and then and then we also want to assume, okay, actually, let's do it this way. Let's not start that way. We're going to assume that, but let's say it this way. Suppose that B and C are in Z and P divides BC. Then BC is congruent to 0 mod P, right? BC is congruent to 0 mod P. So BC equals 0 in Z mod P. By part 2, or by part 3, actually 3, we have that B equals 0 or C equals 0. All these brackets are hard to write. Okay. But this implies what? if B, if this congruence class of B is equal to the congruence class of 0, what does that mean? That means that B is congruent to 0 mod P, right? And being congruent to 0 mod P means what? So that implies that P divides B or P divides C. Right. And so by that theorem, P is fine. Yeah. So again, yeah, you don't have to necessarily know the numbers for the exam, but you need to know that result, that we have that result. Okay, so we've done it. So we proved that 1 implies 2. We did it on Friday. We proved that 2 implies 3, and we proved that 3 implies 1. And so with that chain of logic, we can get all the others. We can get that 2 implies, or that 3 implies 2, because I know 3 implies 1 and 1 implies 2. So I've got the both directions on everything now that we've done this loop. Okay. All right, so that's theorem 2.8. Theorem 2.9. Says the same thing you've conjectured before, which is that if P is prime, then every integer or every element of Z mod P has a multiplicative inverse. Okay, so we've said that before. So let's write that down. Oh, put A and N the integers. Well, actually, what this one says is that that when it's relatively prime to the base, whatever you're modding out by, then you are going to have a multiplicative inverse, which we had conjectured that from looking at multiplication tables. Okay. And this is an if and only if statement, so we're going to need to prove both directions. So let's do the forward direction first. So let's start by saying assume that a x equal 1 has a solution in Z mod N. And let's say that solution is W. So what that means is that A W equal 1, which means that A W equal 1, which means that A W is congruent to 1 mod N. Where am I trying to go? I'm trying to get that GCD is 1, right? Trying to get that GCD is 1. That's where I'm heading. So what does this mean? This means AW minus 1 equals N times K for some K and Z. So AW minus N or plus N times negative K equals 1. So I've got this kind of linear combination bit. I want to show that the GCD of A and N is equal to 1, right? Did we have that? I mean, I think from a previous theorem, we have that, right? Oh, low battery. Darn it. Okay. So let me put this in. I guess I don't really need to record anymore because everyone's here now, but I'll just keep recording because why not? Okay. So yeah, didn't we have that from a theorem before? I mean, we had it the other way, but I think it was that our, whatever we called it, porism or whatever? Was that the porism from theorem 1.2? Let's see. Yeah. So if we can write it as a linear combination equal to 1, then the GCD is 1. That was a result of the way we proved theorem 2.1.2, right? Because we know that all of the linear combinations are possible GCDs, and then the smallest one is the GCD, right? So that's how we proved that. Okay, so we got it. Yeah, the book was doing some extra stuff there to prove that that the GCD was 1, but yeah, we don't need any extra stuff. We're good. Okay, so now I've lost my place in the book. Okay. So that implies that the GCD of A and N is equal to 1. Okay. So let's go the other direction. So we're going to assume that the GCD of A and N equals 1. And I want to prove that that thing has a solution. Okay, so why is that?
Could you just work it backwards?
Oh, so what it's saying in the book is that we did it already. When we did the proof that 1 implies 2, we only used the fact that P is prime to show that the GCD was 1. And then the rest of that proof is the same. So if you look back at how we proved that 1 implies 2 from Friday, that same proof will work. So, so we did this. You want to do it again, or would it be helpful? Maybe. Okay, we can. I don't know. So let's see if we can do it again. So we got to the point that we had the GCD as 1. Then we have, okay, so I'll just put this in parentheses and we'll just go on. So we know that AU plus NB equals 1 for some U, V, and Z. And that was by that linear combination theorem that we had in chapter 1. And so then, where do we go? So then we get that AU minus 1 equals NV n times negative V. So that implies that AU is congruent to 1 mod n, right? Well, that means that AU equals 1, right? So U is the solution. To AX equals 1. That wasn't so bad.
That's really just like.
It's, yeah, it's similar. It's backwards of that, yeah. Okay, good. Okay, so that is theorem 2.9, and theorem 2.10 is just basically a restatement of theorem 2.9, but using the idea of units. So theorem 2.10 is called a corollary because it's basically a corollary of this theorem. So we'll say corollary 2.10. The book calls it a theorem, but I don't think it's worth. Let A and N be in Z with n greater than 1, then we have A is a unit in Z mod n, and then we have the GCD of A and N is equal to 1.
I have a question.
Sure.
You're talking about we don't have to worry about like the numbers of the theorem, but if you're asking us to write.
The
out
statement
the
of a
statement
theorem,
of
yeah.
theorem.
Yeah, so I won't ask something like, write the statement of theorem 1.5. So I won't ask it that way.
So you'll say like about the, like.
I'm not sure yet.
Okay.
I'm not
I'm
sure
just trying
yet.
to imagine what it would look like.
I know, right? Yeah, I'm thinking of a couple of ways I could do this. One way is just to not ask you to state any theorems except for the named one is one way I could do that. Another way I could do that is I could say, finish this theorem, and I give the first part and you give the second part. So that's another thing I could do. So I think it's one of those two things is a reasonable way to do that. Yeah. Okay.
Just had so many-
You know it.
We've had so many.
We've had a lot, yeah, in this well, it's been a chapter and a section and 2 appendices, really is what we've done. It's a lot. So, but yeah, I mean, we're getting close to, well, what are we in week 10? So we're getting close to the end. In the last bit of this, we're gonna do chapter 3 and chapter 4, and that's it. So, so we're more than halfway through of this content, so. Okay, and so that's it for chapter 2, really. So that's all we've done. So, let's see, I think I had something on homework 16 that I wanted to do. But maybe I'll do it next time. But there was one on homework 16. Homework 16 kept dancing around this idea that every non-zero element of Z mod n is either a unit or a zero divisor, which we kind of saw that from the multiplication tables, right? It's either a unit or it's a zero divisor. Either it's relatively prime with n or it's not, right? And so we kind of were proving that. And I put something like that in homework 16. And then I was thinking, we just need to prove that in class probably. So I'll probably work on that maybe, I don't know, sometime before homework 16 is due. So we'll work on that. But today I want to get into chapter 3 if we can. So I'm going to start by writing down the definition of a ring. And so basically what a ring is a ring is a set that has an operation with it. So we've seen that when we talked about Z mod n. We had a set and then we had an operation with that set, okay? So a ring is a set, well, actually we had 2 operations, didn't we, with Z mod n? We had addition and multiplication. So a ring is a set that has 2 operations. You'll have some sort of addition type thing, and then you'll have a multiplication type thing, right? And so, so that set could be a set of lots of different things. So in this case, we had a set of integers mod some number, Z mod n, but you could also have a set of matrices. You could have a set of functions. You could have a set of lots of different things, right? And that set just has to have 2 operations on it, and those operations have to behave nicely, okay? And what do we mean by behave nicely? Well, I'm about to write it all down. So we're gonna have a lot of conditions that have to be met on these, on the operations so that it can be called a ring, okay? And then there are some special ones that can be met, and it'll be like a ring with unity or an integral domain or some other things like that, okay? So basically you should keep in your head, a ring is a set with 2 operations that behave nicely, okay? So that's like your, that's an overall way of thinking about it. So what we're gonna do in over the next couple class periods is I'm going to give you all these definitions for a ring, and then we're just going to look at examples, and we're just going to say, okay, well, what if the set is this and the operations are this? What does it satisfy? Does it satisfy all these properties or not? Okay, and we're just going to kind of play around with examples for section 3.1. Okay, so let's write down all the ring properties. And it may not be a surprise to you, but the integers z has addition and multiplication, and z is a ring. Okay, the integer z with a regular addition and multiplication is going to turn out to be a ring. We're going to prove it. But let's write down all the properties first. Okay. When I write down these two operations, I'm going to write them down as addition and multiplication, but it might look different in different sets. You know, addition might look different than what we think of as addition, and multiplication might be different. Like, for example, have all of you had linear algebra? Yeah. Okay. So when you multiply matrices, that's like matrix multiplication. It's a different kind of multiplication, right? And so when I write these down as addition or multiplication, just keep in your mind that that multiplication or that addition might look different depending on what the set is. Okay. So we'll define all those things. Okay. That satisfy the following axioms. So we're going to have for addition, we're going to have closure, associativity, commutativity, additive identity, and additive inverses. Okay, so let's write all that down. So we're going to have closure. So this is for addition. We'll have associativity. We'll have commutativity of addition. We'll have an additive inverse. Or sorry, additive identity. And we'll have additive inverses. So this all deals with addition. Okay, so we'll have all these properties. So we'll have if A and R and B and R, then A plus B is in R. So you can add two things together, they stay in your ring. It's closed under addition. Associativity is if A plus B, or is that, well, it's not written. It's A plus B plus C equals A plus B plus C. So that's associativity. I can move the parentheses around and it stays equal. Commutativity is that A plus B equals B plus A. And additive identity means that there exists an element 0 in R such that A plus 0 equals A equals 0 plus A. So you have some element that when you add it to other elements, it doesn't change them. So that's the identity element. So you just need to show that that additive identity exists inside of your ring. And you have additive inverses. That's for any A for all. Oh, have I shown you the symbol for all? Upside down A? Yeah, okay. So you have this additive inverse. And for the additive inverse, we usually will write the negative in front of it for the additive inverse. For the multiplicative inverse, we sometimes could write like A inverse equals negative A, right here. But like it's the inverse, but it's the inverse with respect to addition. So anytime you talk about an inverse, it has to be with respect to an operation. Right, so this is the inverse with respect to addition. And so it adds to give us the additive identity. Okay. All right, so that's 5. Then 6 is going to be closure for multiplication. And 7, BII. Oh, whoops. I did 6 wrong. Okay, so we have closure and then we have associativity. And these are both for multiplication. So that has to be closed and associative for multiplication. So closure is that A times B equals B times, oh, sorry, closure is if A and B and R. A times B is in R. And associativity is that A times B times C equals A times B times C. Okay. All right, so multiplication does not have to have all of those properties that addition does. Okay, so to make it a ring, it just has to be closed and associative. We don't have to have multiplicative identity. We don't have to have inverses, and it doesn't have to be commutative for multiplication. If it does have those, well, it'll be a special kind of ring. Okay, but it only has to have those 2 to be classified as a ring. So the last one tells how the operations interact with one another. So that is going to be distributive laws. Okay, so for distributive laws, we can distribute multiplication across addition. And we can do it the other way. Okay, so this shows how multiplication and addition interact with one another. Yeah, Colin?
So on those distributive equalities, the second half of it is commutativity of addition, right? Or I mean, the 2 second halves would be equal because you have AB plus AC and AC plus BC.
Yes.
So those would be equal, right?
They would be. Yes, because addition has to be commutative.
Okay.
Yeah. Yeah, so this distributive law is just saying I could multiply on the left or right, and you have to say the left or right bit because we don't have commutativity necessarily of multiplication.
Yeah.
If we had commutativity of multiplication, then I could just move the C over here and we'd only need one of them.
Right. Okay.
Yeah. So that's why we have to have 2, because we don't necessarily have commutativity of multiplication. Okay. So, but if we do have commutativity of multiplication, it's called a commutative ring. Okay. So a commutative ring has commutativity of multiplication. So I'm going to call that a commutative ring. So we'll call it 9. So let's see, how do we do 9? Is IX. Okay, I don't know why I started with Roman numerals, but anyway, here we go. Okay, so a commutative ring is a ring that satisfies this axiom. And that is that A times B equals B times A. Okay, so 10. Okay, so all of these are just for a plain old ring. So any ring has those. And then these are extra ones that could be satisfied that make special kinds of rings. If that makes sense. Okay. So a ring with identity is a ring that satisfies this axiom that, oh, I guess I'm gonna call this 0, 0 sub R. 0 sub R, because it might not always be 0, right? It might not always be 0. It's 0, whatever the 0 is in that ring. There exists a 1R in R, such that so any A times 1R equals A equals 1R. Okay. So the identity element, the multiplicative identity element does commute, but not every other element necessarily commutes. Some elements will commute, some won't. So, and then 11. An integral domain has no zero divisors. Hey, what do you mean? You scared me.
I got looking out of the office.
You did? Okay, here are my keys. My keys are in the office. Okay, just go sit on the floor outside my office and chill. I'm almost done. Oh my, she scared me. Oh Lord, okay. Okay, and then the last one is a field. So XII. Done that right? 9, 10, 11, okay. A field is a commutative ring with identity that also has multiplicative inverses that satisfies this identity for each A not equal to 0 in R. The equation AX equal 1, R has a solution. So a field also has multiplicative inverses. Okay, an integral domain has no zero divisors. And then a ring with identity has multiplicative identity. And then a commutative ring has commutativity of multiplication. All right, so, okay, so let's think about Z with our regular Z with addition and multiplication. So just the integers like we're used to. What properties does it satisfy and not satisfy? Does it have all of these? Closure, associativity, commutativity, identity inverses for addition? Z with our regular, yeah? Does it have closure and associativity of multiplication? Integers with regular, does it have distributive laws? Yes. So Z with our regular addition and multiplication is a ring. Now let's see what kind of a special ring it is. And here's our first example. Z with the regular addition and multiplication is a ring. And what else? What other kind of ring? Okay, is it commutative? It's a commutative ring, right? Does it have identity? Yes. Is it an integral domain? Yes. So Z, our regular Z with multiplication has no zero divisors, right? Yeah. Is it a field? Does it have multiplicative inverses in it? Z? What is the multiplicative inverse of 3? 1/3. Is it in Z? No. So Z is not a field, right? It's not a field, but it is an integral domain. It is a commutative ring with identity, and it's also an integral domain, right? So Z is a commutative ring with identity. Also a commutative integral domain with identity. Okay. In order to get those multiplicative inverses, I need to throw in the fractions, right? So what would be a field? There we go, the rationals. Well, the reals is a field too, but that's more, even more separate. So we'll do another example. Q with the regular plus and times is a field. It's also an integral domain. So is a field have to be does it field have to be an integral domain? I forget. Yeah, so Q is an integral domain. Yeah, Q is an integral domain, and it's also a field. So I guess I'm wondering, does every field have to be also an integral domain? I'm not sure. I need to think about examples to, to convince myself that that's true. I feel like it makes sense, but I'm not sure. Okay, so so those are our first 2 examples. We're going to do some examples with matrices. We're going to do some examples where I just give you some multiplication and addition tables, and you have to see, does it satisfy these things? We'll do yeah, we'll do Z mod P, which we've done. We're going to do Cartesian products of sets with some so we'll do a lot of different examples, and that's basically what we'll play around with on Wednesday and Friday. But I will do one of the problems from homework 16 Wednesday or Friday, one of those days. Okay, sound good? All right, I'm gonna go get myself back in my office.